Now we begin the fourth section entitled Building Actions, Rewards, and Punishments with Simulated Annealing Approach. In this section, we'll first begin by describing the simulated annealing approach, and we'll take a look under the hood at how it works. Then we'll visit an R example demonstrating how to code the simulated annealing approach in R. Then we'll return to Q-learning, and we will implement a discount factor in our Q-learning algorithm, and we'll show you how to do that in R. And then we'll have several Q-learning in R examples that use the discount factor, some with visual displays of the results. So the first video of this section is Simulated Annealing, an alternative to Q-learning. And in this video, we'll focus on what is simulated annealing and how to implement it in R. Simulating annealing, or SA if you will, kind of a unique name, is a probabilistic technique for approximating the global optimum of a given function. Specifically, it's a metaheuristic to approximate global optimization in a large search space. It's often used when search spaces are discrete and large. For example, you might be familiar with the traveling salesman problem. The odd-sounding name comes from annealing in metallurgy. Simulated annealing is relevant to reinforcement learning because there's a way to apply the SA heuristic to consider some neighboring states of S, that is, states S prime, and to probabilistically decide between moving the system to state S prime or staying in state S. Optimization of a solution involves evaluating the neighbors of a state of the problem. It's called a metaheuristic because simple heuristics like hill climbing will move by finding the better neighbor state, and they'll stop when they have reached a solution which has no neighboring states that are better solutions, and thus moving will not lead to a better solution. But this outcome may just as easily be a local optimum, like in hill climbing, where the actual best solution might be a global optimum that you don't have visibility over at that point. Metaheuristics use the neighbors of a solution as a way to explore the solution space, and although they may prefer better neighboring states at a particular point, they may also accept worse neighboring states in order to avoid getting stuck in a local optimum solution. So metaheuristics can find the global optimum if run for long enough period of time, many episodes. In some cases, simulated annealing is considered an improvement over Q-learning. The issue with Q-learning is that you use an epsilon greedy selection approach which relies on a fixed value of epsilon. However, this might not be beneficial or optimal as the learning agent, gains confidence in its state action function and should therefore do less exploration over time, implying that an epsilon value that increases over time might be more appropriate. In the variant with simulated annealing, the probability to take a certain action is proportional to the Boltzmann distribution, which we won't describe in detail, but it's proportional to e raised to the power q s of a divided by t, where t is a parameter that decreases over time. As a result, a larger t makes all actions more or less equally likely, while smaller values of t prefer the current best action according to the state action table. Let's go over to R and take a look at how we can implement simulated annealing in R. So here we are in R. We need our reinforcement learning library, so let's load that up. And the key to simulated annealing is that it replaces the fixed epsilon e-greedy action selection criteria with probabilities that are derived from the Boltzmann distribution. So we're going to have to modify a few of our functions. However, we're going to use the same 2x2 grid simulate environment function. Okay, now here is our previous learn episode function from Q-learning. And I just put it up there so you can refer back to it if you want to, but we're going to modify this. Note, in the previous version, we implemented the eGreedy selection criteria in these statements here. So we're going to replace this function, and we'll call the new function learn episode SA, and we're going to include some new parameters, specifically n and I, that we'll explain in just a minute, some new formal parameters to our learn episode SA function. So just as we did before, we initialize the state to the starting state, but instead of eGreedy, we're going to incorporate t, which will be defined as n divided by 20 times I. And then instead of implementing the eGreedy selection, we're going to do this. We'll say, while we're not in the terminal state, we will first of all initialize the Boltzmann distribution with this expression, and then we're going to set the probabilities that we're about to use in the sample function from the Boltzmann distribution. And then the action that we take will be sampled from actions and will be derived from probabilities that we just determined up here from the Boltzmann distribution. And then we'll call our existing simulated environment function, and we'll use the existing update rule for Q-learning. And we will return here the movement to the next state, and then we'll return our updated Q. Okay, so we're borrowing from Q-learning, but instead of using the epsilon greedy, we're deriving probabilities of selecting an action from the Boltzmann distribution. Okay, so let's grab that function. And then we'll use similar previous R code. There's our actions, up, left, down, right. Here are our states. And we'll use the same environment function to model our 2x2 grid. So let's grab that, make sure that's loaded in memory. And here's our Q-learning function, and it has changed slightly by these lines of code here. Okay, so we're going to perform n episodes, iterations, using t and the Boltzmann distribution. And we're going to use n episodes. And so n and I, and we saw them as formal parameters up here in the learn episode function, really all they are n is the number of episodes, and I is the first episode because it comes from this. Okay, and then we in this function we're calling learn episode and we're returning Q, and it gets Q from the learn episode SA function. So let's load that up, grab that, and we use our original epsilon values, learning rate, alpha. Let's set the seed, and then let's run Q-learning, but recall it's been, the epsilon greedy has now been replaced with drawing probabilities from the Boltzmann distribution using that t parameter. Okay, so we do that, and let's pull this over a little bit so we can see our state action table. Now, if you come down here and we quickly go to the policy, down, right, up, left, this has not changed. The optimal policy is unchanged. But what you find is that the best state action values are more prominent and more, there's much more variance, distinction between the optimal choices in each state, the optional action choices in each state. For example, if you're in an SO, down is 8. If you compare this to the previous state action table, you'll see that the disparities in the numbers are much higher. Okay, and S1 right is 9, S2 up is 10. So in this case, drawing the probabilities from the Boltzmann distribution gives you more discriminatory power in determining the global solution of action choices.